Let's go back to the third part of the lecture. So we mentioned the general idea of the variational autoencoders. So just now we mentioned that in order to build a good general model, we need to model the distribution of the px. And in order to implement this idea, it would be so the real generative process actually can be constituted of two steps. The first step is that we know some some margin distribution of the pz, and we sample point, random point from the pz. And then if we can also learn at the same time the distribution of the px given z, which actually plays the role of the decoder, and then we can try to project the representation learned in the latent space in our input space, and to in such a way to generate different kinds of the input data. And we have mentioned that in the suppose that it's a linear model, which means that the px given z is just the x given z is just by some linear transformation wz plus mu, and then all the distributions, the px given z as well as the posterior distribution of the pz given x all follow a Gaussian. So this can significantly reduce the difficulty of our problem, because Gaussian, the integral of the Gaussian, all are Gaussian distributions. So in this way, we can, although we can get get some solution, but maybe the modeling capacity is not as good as we expected. So the problem currently that if it's possible, such that we consider that the px given z is not just x given z is not by linear mapping, it's not as expressed as the wz plus mu, and suppose that the w is a parameters of the of any model, of any decoder or any neural net or any machine learning model, but the thing that kind of we model the relationship between x and z, instead of using the w z plus mu, we say that it follows a nonlinear mapping. The x equals to the f of the z and the w. W is a parameter. F is any kind of the nonlinear mapping or linear transformation. And in this way, although we know that the z is a Gaussian, even though it's undergo some complicated transformation, or the nonlinear transformation, for example, the f here, the px given z may still follow a Gaussian distribution. This is good news. But the thing that we also need to, another big problem is that currently it becomes a bit hard to model or to express the px, which is the integral of the px given z and the pz. So this can be very, very hard to get analytical expression to express the px here. So which means that we still do not have a good way to generalize the model in this way. The thing that we do not assume we assume that the marginal is a normal distribution, and the normal distribution, even though it undergo some nonlinear transformation, it may still follow, in principle, still follow the px given they still follow Gaussian distribution. But the thing that currently it's a bit hard to express the mean and the variance in an elegant way, because the mean and the variance may be very, very complicated, which is controlled by our nonlinear transformation. So we move to maybe the most important topic in today's lecture, and we give, although at first it looks a bit complicated, but we're trying to give one step-by-step derivation to help you to have a better understanding. So the thing that we first introduce. In principle, we want to, the theta is a parameter of our neural networks. We want to maximize the log likelihood. So which means that we aims to maximize the log of the px. And we know that the px by the Bayes rule, it equals to this one. The px by the Bayes rule, it means it can be expressed as the integral of the px given z by pz and the integral over the z. So this is the Bayes rule told us. And then the second line of the equation indicates that we just multiply all the term inside the integral, but multiply by 1. But in order to build the 1, we see that we introduce a variational posterior distribution, and the 1 equal to the p phi z given x divided by p phi z given x, because the numerator and denominator are the same. So together, the ratio is still 1. So in this way, which means we can move from the first to the second line. But the role of the variational posterior is we expect that it can be used as an approximation. Here, the p phi z given x. Expect it can be used as an approximation to the real posterior distribution of the pz given x. So the idea we call that we first assume that we have a margin distribution pz. The z is the latent codes, and then we use a decoder. The decoder is of the parameter theta. We can obtain the distribution of the px given z, and then if we in some way we can learn both the px given z and the pz, maybe we can also get the px. And then we can also get the posterior distribution of the px given pz given x. Pz given x can be understood that how to learn the latent code given different input samples. But the thing that the pz given x usually it's because if by the Bayes we also need to. But the thing that in order to obtain the p theta z given x, we still need to get the px first. But in principle, it's very, very difficult or even impossible. So our general idea is that instead of explicitly model the inverse of the mapping, the p theta x given z provides the mapping from the latent codes to the input space. Ideally, we want to have a way to model the inverse of the mapping from the x to the z, go back to the z. But in order to do the precise inverse, maybe we have some mathematical problem. So the general idea is that instead of directly use a neural net, ask the neural net to model the inverse, ideal inverse of the mapping pz given x, we assume that we have another neural net or another mapping. We call this mapping as the q. It's parameterized by some another neural with the parameter phi, and we assume that the q phi z given x plays the same role as the q theta z given x. So you can feel that. We assume that they are as close as possible or almost no difference, but it's a new model, new neural net, or new distribution. So we introduce the variational posterior distribution to mimic or to play the role of the p theta z given x. So we assume that now we have a variational posterior distribution q phi z given x, and the ratio of the q phi z given x by the q phi z given x is equal to the 1. So there's no problem from the first line of equation to the second line of the equation. Now we move to the third one, the larger or equal to. Actually, this derivation is a bit more complicated, in which we use but it's a very well-known inequality in statistics, which is called the Youngson's inequality. In principle, it expresses that the log of the expectation over distribution Q should be larger or equal to the expectation of the log of some function over the distribution of the Q. So by just use the Youngson inequality we can derive from the second step. From the second step to the third step. So it means that the log of this quantity is larger or equal to the integral of the Q phi z given x. Q phi is our posterior distribution or variational posterior distribution that we want to mimic, or the p theta z given x, and it should be larger or equal to the Q phi z given x log of this quantity. And then we all know that the the log AB we can divide by the log A plus log B. So it means that the log of the p theta x given z and the p lambda z by Q phi z given x, it will be equal to the log of the p theta x given z plus the log of the p z by Q phi z given x. This is variable property of the log. And then which means that we can kind of have two integral terms. And finally, we obtain the last equation, and the first term is exactly can be expressed as the expectation of the log of the p theta x given z, which is the expectation it's over the distribution of the Q phi z given x. On the other hand, the last term, it equals to the integral of the Q phi with the log of the Q phi by the p lambda. And so this is the last term, which actually in machine learning, this is called the KL divergence, by Kleibler divergence. So the divergence means that we want to, in some way, to quantify the distance of these two distributions. So let me show why this can be used to quantify the so we just have yes. Second line, third line, okay. Oh, it's a very good question. In principle, we want to maximize the log likelihood. So we want to maximize the log of the p theta, but explicitly maximizing it may be difficult. So maybe we can consider maximize a lower bound of this quantity. So maybe this is the level of the log of the p theta, but it's very, very hard to directly model it. But we suppose we know lower bound, maybe there is a gap between the true value and the lower bound. But in principle, if we can try to guarantee that the lower bound is as maximum as possible, then we can still guarantee intuitively trying to make this as big as possible. We do not we do not say it's a proportional. We see that there is a probability, there is a gap, but later I will show the mathematical formulation of this gap. But the thing that there is a gap between these two quantity, and we do not say there is a ratio. We do not say this is proportional to low bound, but we just say the true value and the third line of there is a distance, and the distance is controlled by some others. But the general idea is that maximize this is extremely difficult, but we try to maximize the lower bound as much as to. So intuitively it can be answered. makes sense. Another general idea, although not mentioned in this lecture, but also widely used in deep learning, is that we can also try to suppose this other one. But we do not derive in this way. Suppose there is upper bound of the log of the p theta. Another general idea also widely used in machine learning is that we try to minimize the lower bound, the upper bound as much as possible. So both ways can be understood as an alternative way to max to somewhat but the thing that general idea is to minimize some quantity. So the thing but is not used here. But the thing that things our currently the general idea to maximize this quantity, so we can instead try to maximize the lower bound as much as possible. Yes, exactly. So we need to, the assumption is that we need to guarantee that the lower bound, the gap can be as close as possible. We also need to understand what is the gap here, but I will later show what is the gap here. So in principle, you can derive different kinds of lower bound, but not all the lower bound are useful. You need to pick the maybe a best lower bound and try to maximize it as it. But you also need to understand what is the really gap. So, yes. And yes, we just mentioned that the first term can be understood is the expectation of the log of the p theta x given z, and the expectation is over the z. And the second term is actually expressed as expectation of the log of the p lambda by the q phi z given x. But in machine learning, we call this term as a KL. The second term. Yes. By the q phi z given x. So we see that there are two probabilities. The first probability is p theta x given z. The second probability is the probability ratio. Okay. So now we see that the second term, people call it the KL divergence, and it's widely used in different machine learning, deep learning, and lots of AI application. Why it can be used to quantify the divergence? You can understand the way to quantify the closeness of two distributions. Why we can use the expectation? Usually the KL divergence is expressed as log and so this is a KL divergence between two distributions P and Q. Why it can be used to quantify the distance? The distance is to the closeness of two distributions. That suppose now assume that the P equal to the P, then we can see the inside the log is we have the log 1, but we know that the log 1 is always 0. So even though we integral over the 0, it still gives a very small near 0 value. So this is so which means that it can. But in the next lecture, we will go relatively a bit deeper about the divergence measure. But here, in today, you just think about this is a very intuitive way to quantify the difference of these two distributions by model the ratio of these two distributions P over Q. So log P over Q and take the expectation equal to the K divergence between Q phi z given X and the P lambda, the prior distribution of the PZ. So which means that yes, and in variational autoencoder, we call the last line of the equation as the evidence lower bound. So there is a terminology called this quantity. The first is expectation of the log of the p theta x given z, and it can be intuitively understood as a way to quantify the reconstruction performance, because you can imagine that the physical meaning of the first term is that I sample, suppose there is x to z and to the x hat. The x hat is our reconstruction or generated image, and the q phi z given x provide the mapping from the original space to the latent space, whereas the p theta x given z provide the mapping from the latent space to the original, or to the go back to the latent space. So the physical meaning of the first term, the reason why it can be used to quantify the reconstruction, the quality of the reconstruction is just we assume that currently the z, we sample a z from the latent space. The latent space is generated by the q phi z given x, and then we go back to reconstruct a new data by the mapping function p theta x given z. So it explains in the first term, it can be somewhat understood as an intuitive way to measure the quality of the reconstruction. But the second term is usually people call it understood as a regularization term to kind of somewhat measure the distance between the margin distribution of the z and our posterior distribution, the q phi z given x. But it's just the terminology, people call it as a evidence lower bound. And in autoencoder structure, there is a very close physical meaning to one each of the term. The q phi z given x is our encoder. It indicates the mapping from x to the z, and the p theta x given z, it's a decoder. It describes the way to generate x from the latent codes. And the p lambda, it's a marginal, also people call it a prior distribution. So the logic is that we have a flow from x to the z and to the x hat, and we assume that there is a prior distribution on the margin distribution of the z. So we assume, usually we assume that our latent codes follow a Gaussian distribution because it can significantly simplify the training of our model. So which means that the loss function of the objective of our variational autoencoder is to on the one hand trying to make the reconstruction as much as possible, as perfect as possible. On the other hand, also trying to somewhat regularize or minimize the distance between the prior distribution and the posterior distribution of the PZ given X and the P lambda is up. So now we use another way and trying to answer the question that just raised. How close is the gap between the maximum P log theta and the evidence lower bound? So then we need to introduce another way of derivation. So on the first, we know that the P theta log of the Px equal to the expectation of the Px over z, because the z and the P theta are somewhat independent variables. So so it does not. So this is by the mathematical property, and so then again we multiply the term in the P theta x multiply by a value of the 1, but now the one is a ratio of the p theta z given x by p theta z given x. And then by the Bayes rule, we know that the p theta z given x and the px equal to the joint distribution of the pxz. Yes, this. So this is by the Bayes rule, we know that. And then we do another derivation, and we multiply this quantity, the numerator and the numerator and the denominator of this quantity, and we multiply by both with the q phi z given x, and we get the third line of the equation. But all the things are relatively straightforward, and then because still we use the property of the log of a by b equal to the log a plus log b, and then we can have two expectation terms. And we follow and use the straightforward derivation, and the final expression is like this. So this is very interesting, because if you look carefully, the first two, the evidence lower bound that we just mentioned, the third term tells us the gap, how close of the lower bound to the ground truth, and the gap, it's the KL divergence, again, another divergence between our posterior distribution Q phi z given x and p theta z given x. So I'm not sure if you have followed the logic. The logic is that the reason we want to, in the second line of equation, we want to maximize log likelihood of the px, but the thing that we see that in this way, and we need to also intuitively, if we want to also learn the encoder function, which if we want to also have a good way to learn the real posterior distribution of the pz given x, it would be very, very good. But we know that in doing so, it's very, very hard. So our general idea is that we want to introduce a new distribution. We call the new distribution as an variational approximation. The new distribution is q phi z given x, and we assume that the q phi z given x is as much as possible as close to the p theta z given x. Now, by introducing a new the variational approximation, we introduce a q phi z given x, and then we derive our evidence lower bound. But the idea is that we expect that the q phi z given x is as much as possible to the real posterior distribution p theta z given x. And now the final derivation indicates that the gap between our lower bound and the real p theta given x is actually controlled by if our approximation can be as close as possible to the true posterior distribution of the pz given x. Pz given x is something it's hard to judge, hard to train, hard to model. This explains why we introduce an variational approximation. We call it q phi z given x. So the final derivation told us if our approximation is as close as possible to the true posterior distribution pz given x, then the lower bound is the same as our ideal objective, the log of the px. So this also explains that on the one hand, by maximize, so it also told us by maximize the evidence lower bound, we can try to close the gap. And then by close the gap, we can guarantee why we can realize implement this by just maximize lower bound, because they are synergistic to each other. Yes. Exactly. Yes, exactly. So intuitively is that if the Q phi z given x, if the distance to the true p theta z given x can be as small as possible, it also means that if the gap is small, and it also means that it explains why we can try to maximize this by just maximize a lower bound. So it's so they are synergistic to each other. And so now maybe on the next lecture we will just introduce how to maybe practically implement a real variational autoencoder, but the most important thing is to understand the derivation behind these two ways of derivation, and understand the most important thing is to on the one hand understand the derivation in this equation, and also understand the correspondence between which distribution correspond to the encoder and which distribution correspond to the decoder, and also understand the physical meaning of prior distribution. And this constitutes the objective of the rational autoencoder, because we use the autoencoder structure, and also because we introduce the rational approximation. So why people name it as a rational autoencoder, and also would much better to understand that by maximize the evidence lower bound, this is objective we want to maximize. We are actually trying to guarantee the gap as close as possible to the true value we want to optimize. And the gap, the physical meaning that we expect our approximation is as close as possible to the true positive distribution, although the true positive is hard to model from.